If we move the armature, there is an increase in the voltage. To maintain the magnetic neutral axis, we have to shift this slightly using opening this knob, this screw, and shift this slowly to get a 0 over this particular voltage should be 0. It is almost 0 because now the machine is in the accurate position, but if the axis is misaligned to the neutral axis, this brush holder is moved in such a way to keep it to the magnetic neutral axis. Our next experiment will be rotating magnetic field, that to verify the generation of three-phase rotating magnetic field by means of three-phase current, to invert the rotation direction of three-phase rotating field, to verify the generation of single-phase magnetic field by two pulsating fields, and to invert the rotation direction of single-phase rotating field by varying the connection of auxiliary phase. For this, we want components: alternating current stator. This is the alternating current stator. Magnetic probe, power supply, electronic measurement module, and rheostat module. Now, first we will make a three-phase machine circuit as shown in figure. This is the figure which we have to make. We have to make connections as per this figure for three-phase rotating field in only stator. Here we have made the connections as per the circuit diagram for experiment number 7. L1, L2, L3 for power supply. Here we have 24 volt power supply. Here we have 24 volt power supply. Now I have to select 24 volt, A 24 volt. Now the stator is being energized. I put this magnetic probe inside the and one can see that our magnet is rotating with the applied field. The direction of the rotation of motion is clockwise. If we want to change the direction of rotation, then what we have to do is just change the phase sequence. And again I am putting the magnetic probe inside the stator. Okay, and one can see now the magnetic probe has started rotating in different direction. So this verifies that field direction is reversed. For single phase rotating field, we have to make the connection as per this diagram. So first we make the connection. We have connected the circuit for single phase motor, which is a capacitor motor. Initially this switch is kept closed, and after the motor is run, then it is kept open. So we have connected by using a single phase variable supply for 10 volt. So let give it from 0 to 10 volt AC. Now I increase the voltage and insert the probe inside the cavity, and you can see the magnetic bar is moving in one direction. कैपेसिटर जीरो पे कर दो. It is moving in one direction. Okay. For reversing the direction, the terminals of V6 and U6 are interchanged and the direction of rotation will change. So this concludes our 7th experiment. Experiment number 8, 3-phase squirrel cage motor, 2 poles, 24 volts, delta connected. To delta connect the stator winding, to start the motor with direct connection to the mains, and to record the operation characteristics of the motor. The components required are AC stator and squirrel cage rotor. This is the AC stator, and this is your squirrel cage rotor. We will insert this rotor to the AC stator. This is the connection diagram which we have to make, and if one finds it difficult to make through this connection diagram, one can use this diagram also. Now for operational characteristics, we have to use a electromagnetic brake unit. This is the electromagnetic brake unit. It is mounted on this adapter bracket using these Allen screws. A load cell is mounted here like with help of these screws, and the wire from load cell is going to terminal K. Wire from this 5-pin connector K2 coming from the speed sensor. So this is how K will be responsible for torque and K2 will be responsible for RPM. And there is one more thing. This electromagnetic braking magnetic braking mechanism will require 0 to 40 volt DC supply on these terminals, plus and minus terminals. So now we make the connections accordingly for 3-phase squirrel cage motor running in 2 poles, 24 volt, delta connected. Now we have connected our machine as per the circuit diagram, and here we want 24 volt input. So we will select 24 volt input and we will start the machine. Okay, the machine has started. We can see the values for current. The upper P power and the lower power should be added. This is the absolute values. So voltage, current 2 amperes and power 43 plus 8. Here, as it is a 2-pole machine, the RPM is around 3000 and we have not applied any torque, so the torque is 0.02. Now we will apply torque. Here we have to connect it to 40 volt DC, 0 to 40 volt DC, and slowly increase the potentiometer, so we can see the increase in torque. As the torque is increased, the RPM is decreasing. Here our motor is running, and these are the values of current. Current, voltage, power. These are the values of current, voltage, power, RPM and torque. Now I increase the torque. So for different values of torque, now we have increased the torque. The RPM is going down. We have to take readings up to value of torque 0.488, not more than that. And we will get voltage, current, power 1, power 2, addition of power 1 and power 2. Cos phi will be given from the formula. This is the RPM. This is the RPM. Now this is the power output, which can be calculated using the formula, and this is efficiency, which can be calculated using the formula for efficiency. So from that we can draw the characteristic curves of the motor. Now we will go for experiment number 9, 3-phase squirrel cage motor, 2 poles with 42 volts star connection. The diagram of this, we have to make the connections like this diagram. So first we make the connections. We have made the connections as per the drawing. Now here we want 42 volts in the input side as per the drawing. We need 42 volts as per drawing. So we have selected 42 volts, and now our motor is in the running, and here we can have electrical parameters and mechanical parameters, and rest is same as we have done previously for 3-phase motor in the previous connection. So just we have to increase the DC. And the load is increased. We increase the DC, decrease the DC, load is decreased. So this is how electromagnetic braking works. Next experiment is 3-phase squirrel cage motor, 2 poles, 24 volt delta. The connections, we have to do the same experiment with the same connection winding connections. Just we have to change these connections on the motor terminals, and this is the loading arrangement. The procedure is same, just we have to change the connections of motor, and we have to load this up to 0.96 Newton. Next experiment is 3-phase squirrel cage motor, 4 pole. Now we will do a 4 pole motor because others were same. Now we will do 4 pole motor with 24 volts delta. So here it is we are using star delta starter, and these are the connection diagrams. So according to connection diagram and using the star delta starter, we will make the machine for 4 pole. We have made the connections according to this diagram for making 3-phase squirrel cage motor 4 pole 24 volt delta. Now we have made the connections. The power supply would be required is 24 volt. So I select 24 volts. Now we will go to star delta starter and will first switch on this power supply. Then we'll move to star delta starter. Here the motor will start in star connection. We can see the currents over here. The motor has started in star connection and we can see the currents over here. These are the currents. So it is a lesser current. Now we will put the motor in delta connection using this switch. Now the motor is in delta connection and we can see as soon as we go to delta connection the current is increased. Likewise the same in previous experiment where we have gone for loading the machine. We will load the machine using same technique by increasing this DC supply to the electromagnetic brakes, and this will increase the torque. We can see that the torque is increasing as I am increasing the DC supply to the electromagnetic brakes. Likewise we have to take readings to tabulate in this graph, and we can go up to 0.997 Newton meter torque. Now for experiment number 13, 3-phase squirrel cage motor, 4 poles, 42 volts star connection. So the equipments required will be the same, just what we have to do is change the connections over here, and this will come from delta to star mode. So we will change the connections as per this diagram and run the motor again. Now for experiment number 13, 4 pole machine, 42 volts star connection. The connection diagram is shown here. 42 volt is required. Now we will pull it to the 42 volts. 42 volts. Start the 42 volts. The machine is running, and these are the current and other parameters. The machine has started running and we can see these are the parameters. For load test, again same, this is the electromagnetic brake coupled to the machine and the test, and from here we will increase the DC and we can see the torque is increasing and the RPM is decreasing against it. So likewise we have to make a table. We have to make a table again. Likewise, now we will go for single phase motors. Now we will go for Dylander motor, that is a 2-pole motor. So we have connected the motor as per 2-speed Dylander motor, for which will work in 4-pole and 2-pole both simultaneously using the pole changing unit. So for that we require power supply 42 volts. Now we will start for 42 volts, and from here pole changing unit will switch on the supply. Motor is started. RPM is 1500 RPM, so it is running in the 4-pole mode. Now I am changing it to another mode. The motor is running at a very high speed, that is 3000 rpm. It is running in 2 poles. So this is called the Dylander machine, which can run in 2 speeds as required using a pole changing switch. Experiment number 15, split phase motor. To start the motor with resistive auxiliary winding, to record the operation characteristics which are the same as we have done in 3 phase. What we require is AC stator and squirrel cage rotor, load and rheostat module, power supply, electrical measurement module, mechanical module, adapter support, electromagnetic braking. The connection is like this. So from U1 to U6 is the main winding, and this would be the auxiliary winding with a switch over here. This switch is initially closed, and when the motor is run, the switch is opened, so the auxiliary winding circuit is disconnected and motor will run on only the main winding. And this is the circuit for electromagnetic brakes, which we have done in previous experiments also. So here first we make the connections for this. Here we have made the connection for split phase motor, and the supply required is 42 volts. So we have selected 42 volts. Now I am starting it. The motor is started. These are the initial currents and voltages. Now initially we have to keep this knob at 1, and when the motor is run, we will remove this resistance from the circuit. So we can see here the current is reduced. Now for load test, same using the electromagnetic brakes as we have done in previous examples. We would load the motor using the DC supply, and if as I am increasing, you can see the load is increasing and the RPM is decreasing. Same wise we have to take the readings and tabulate in the graph. This will give the load characteristics of this single phase motor. It is a split phase single phase motor, and here it is mentioned in the manual we can go to up to 0.492 Newton meter maximum. Next is capacitor start and capacitor run motor. Next is capacitor start and capacitor run motor, for which the diagram is like this. We have to make the connections as per the diagram. So now first we make the connections. The connection for capacitor start and capacitor run motor are completed. So here we will require 42 volts. We have selected 42 volts. So we first in this mode, here we have to keep this knob at 1, 2, 3, and as soon as the motor starts, we will go to the 1. So only one capacitor will be in the running mode, and the starting mode there will be 3 capacitors in the parallel connection. See here, we will select 42 volts. Now see, the motor has started running. The initial current is 6.9. Now I am first capacitance I have cut down, and now it is on the running capacitance. This is motor with capacitor start and capacitor run mode. Now for the load characteristics, we will have to do the same methods This is the electromagnetic brake, and we have to put DC supply on it, variable DC supply on it, using this knob and keeping it in the C mode. And as soon as I start increasing the DC supply to the brakes, the torque increases and the RPM decreases, and so here the current also is increasing. So this is all about capacitor start, capacitor run motor.